Welcome to an example on how to solve a log equation that also requires the use of the quadratic formula. Looking at the given log equation, if we combine the two logarithms on the left, or these two logs here, notice how we have a sum of two logs, then we can write the log equation as an exponential equation to solve for x. And again, because we have a sum of two logs with the same base, we can take advantage of the product property of logarithms given here, where if we have a sum of two logs, we can write them as a single log if we multiply the number of parts of the logarithms. Which means the left side of this equation is equal to log base 3 of the quantity x plus 2 times the quantity x minus 1. And this is still equal to positive 2. Now that we have a single logarithm on the left, we can write this log equation as an exponential equation, recognizing that the base is 3, the exponent is 2, and the number part is this product here. So 3 raised to the second power must equal this product. Therefore, 3 squared equals the quantity x plus 2 times the quantity x minus 1. Notice how we have a quadratic equation, so now we're going to multiply out the right side and then set this equation equal to 0. Well, 3 squared is 9, and then here we'll have 4 products, 1, 2, 3, and 4. So x times x is x squared. X times negative 1 is negative 1x, or minus x, and then plus 2x and minus 2. So here we have two like terms. So we have 9 equals x squared. Negative 1x plus 2x is 1x, so plus x minus 2. Let's set this equal to 0 and see if it's factorable. So if we subtract 9 on both sides, we have the equation 0 equals x squared plus x minus 11. Now earlier we had a problem just like this, but this was factorable. But notice how in this case this is not factorable because there are no factors of negative 11 that add to positive 1. Which means to solve this, we'll have to use the quadratic formula. So let's go ahead and finish this on the next slide. So again, here's the equation that we want to solve. Notice how I did flip the equation around, which doesn't change anything. So the first thing to recognize is that a, the leading coefficient, is equal to 1, b, the coefficient of x is equal to 1, and c is equal to negative 11. So a equals 1, b equals 1, and c equals negative 11. So now we'll sub these values into the quadratic formula. So we'll have x equals negative b, or negative 1, plus or minus the square root of b squared, or 1 squared, minus 4 times a, which is 1, times c, which is equal to negative 11. This is all divided by 2 times a, or in this case 2 times 1. So we have x equals negative 1 plus or minus the square root. And we need to be careful here with the discriminant. 1 squared is 1, and this is going to be minus negative 44, or plus 44, divided by 2. So we have x equals negative 1 plus or minus the square root of 45 divided by 2. Now let's see if we can simplify the square root of 45. Well, 45 is equal to 9 times 5, and the square root of 9 is equal to 3, so this simplifies nicely to 3 square root 5. Therefore, we have x equals negative 1 plus or minus 3 square root 5 divided by 2. Now remember, this represents two solutions. One solution is x equals negative 1 plus 3 square root 5 divided by 2. And the other solution is x equals negative 1 minus 3 square root 5 divided by 2. Now before we check our solutions, let's get the decimal approximations for these values. This first solution is approximately 2.8541. And the second solution is approximately negative 3.8541. Now to check our solutions, the main thing to remember is that the number part of the logarithms, or the arguments of the logarithms, which would be x plus 2 and x minus 1, must always be positive. So notice if we take a look at the solution that's approximately negative 3.8541, both x plus 2 and x minus 1 would be negative, and therefore this is not a solution to the log equation. And therefore we must exclude this as a solution. But notice how when x is approximately 2.8541, both x plus 2 and x minus 1 would be positive, and therefore this does check as our solution, and we have one solution to our log equation, which would be this value here. Again, we have the exact value and the decimal approximation for our solution. That's going to do it for this example. I hope you found this helpful.